We are Canadian Society of Iranian Engineers and Architects. We have been established close to 40 years ago, and ever since we have been working and giving service to the society. We are a non-for-profit organization, and we strive for technical, professional, scientific excellence, as well as our cultural gatherings and cultural activities that some Farsi-speaking members will enjoy during the year. In our organization, we have several committees. One of them is a civil group, which is dedicated to civil engineers, and we have monthly meetings, most of the times last Wednesday of every month. It is like 8 years that non-stop we have had these sessions, and we have got very good feedbacks. Tonight, we are very happy to have a valued speaker, Mr. Nader Shukufi, who is a structural engineer with over 2 decades of experience. He has held key roles in reputable firms and currently serves as the senior structural engineer at WSP Canada. Nader obtained his degree in structural engineering from Sharif University of Technology in Tehran. Throughout his career, he has played a significant role in the design of notable structures, including cinema complexes and mega malls and a lot of other big projects I see here, Bandar Abbas Airport and Muscat Olympic Shooting Complex, etc. And also Nader has earned a few prestigious awards, such as the Young Professional of the Year Award from FIDIC, which is the Federation International of Consulting Engineers, and the Outstanding Engineer of the Year Award in Iran. In addition to his professional achievements, Nader is actively engaged in various professional organizations. He has served as chairman of FIDIC Young Professionals Forum and has contributed to several committees focused on sustainable development and capacity building. I will not hold you anymore, and I would ask our valued speaker to please take over. Nader, we are all ears for you.
Thank you, Afshin, and good evening, everyone. I want to start by expressing my gratitude towards the Canadian Society of Iranian Engineers and Architects and the Mohandes Civil Group that provided the opportunity for this presentation. The idea for this presentation was seeded when we were discussing the collapse of the Baltimore Francis Scott Key Bridge. In that discussion group, we were talking about what might have happened to that bridge and what was the sequence of the events that led to the collapse of that bridge. What happened first, what was the consequences, which element failed first, and how and why it led to the failure of the second element, and things like that. That was when Afshin decided that it might be nice to talk about the overall idea of a sequence of failure in the structures and asked me to present it. I don't know how many of you are fans of crime TV series. Well, me, I'm a big fan. I've watched almost all crime TV series there are. And a common trend in these series is that there is a clever detective who goes around, gathers evidence, and finally, in a climactic moment says, here's what happened. Well, we have a similar approach when we're looking at a collapsed structure. We go around, gather facts, write some possible scenarios, do some analysis, and finally we would say, here's what happened. And from that, We learn some lessons that we will apply to our future designs, hoping to prevent a similar catastrophe from happening. But that a posteriori approach is not all that we do. We also have an a priori approach in which we try to predict what might happen and prevent it from happening. There are some words that are going to be repeated a lot throughout this presentation. Words like redundancy, collapse, progressive collapse, resilience, and here are some definitions. Well, actually, the first word, resilience, is not going to be repeated much, but it's a very important term. Resilience is the ability of a system to absorb a shock and to retrieve normal activities after the incident. These days, you hear a lot about it, mostly in personal and psychological terms, but it's mainly a tool in systems analysis. And in our profession, it is a very important aspect of infrastructure design. The subject of resilience has become mainstream in recent years, especially when noticing the effects of climate change that is causing more natural disasters and brings a focus on how our infrastructure might react to these new severe cases. Well, resilience is different from stability, a system that becomes unstable for a short period and with minimum damage and gets back to normal in a relatively short time will be considered resilient. Structural redundancy is the ability of a structure to withstand changes in boundary or support conditions, or failure of one or few members without a collapse. A major contributing factor to redundancy is the level of indeterminacy of the structure. And being indeterminate is not enough to be redundant, but a redundant structure is always indeterminate. I will be using the words collapse and failure a lot during this presentation, and I would use them sometimes interchangeably. But there's a slight difference between these two. So, for example, a beam that has been cracked beyond
We all have problem with communication of another. I hope it will resolve shortly.
different definitions, and one of them is from an AISC document, and another from the GSA, that is the General Services Administration, both American institutes. Keywords of both definition is that the final collapse is disproportionate to the triggering event, and that there is a sequence of collapses. So the AISC defines it as collapse of all or large part of a structure precipitated by damage or failure of relatively small part of it. And so it considers that what triggers it as a small event, and there's a chain of events, and it's that some sort of a butterfly effect, that a small event somewhere causes a very large result in somewhere else. The definition by GSA is very similar to that. And and I will be quoting the GSA a lot during this presentation. And it goes on as the progressive collapse as a situation where local failure of a primary structural component leads to the collapse of adjoining members, which in turn leads to additional collapse. Well, I mentioned that a progressive collapse is one where the final damaged area is disproportionate to the triggering event. To measure the level of disproportionality, we define a term as degree of progressivity, and that is the ratio of the final damaged area to the initial collapsed area. And so, for example, for the Ronan Point building that we would see later on, this degree is 20, and for the World Trade Center that we would also talk about later on, it's 110. Progressive collapse is not always avoided, and we sometimes look for it intentionally, especially for controlled demolitions. And here is an example of it. Unfortunately, I don't know where this structure is and what is the original source of the video. I just saw it somewhere in the Instagram. But most of the time, the progressive collapse is not that soothing side of intentional controlled demolition, and it's mostly a catastrophic event. I apologize for sharing this video that might be a painful reminder for some of us of the horrific collapse of the Metropole building in Abadan that resulted into 43 deaths and scarred the nation. I will not discuss the collapse in this presentation, and I will just note that the incident mostly highlights the importance of professional ethics. Almost every stakeholder in this project, apart from the original consultant and partly the inspector, have gravely neglected their duty to the public, and there have been huge errors in design and in construction of the project. That's the severity of which made the demise of this structure inevitable. So I will now review some historic cases to help us understand what has happened and how we might be able to prevent similar events in the future. And I will start by a mythical story of Senemar's brick. It is said that the story happened during the Sassanid era in what is now known as the Levant in somewhere south of Turkey. And the architect, Sanamar, built the most beautiful palace of the world for the king of that province. The palace was named Khovarnak, and there was a single brick in it that, when pulled out, would result into the collapse of the entire palace. Sanamar was killed by being thrown off the same palace, both as a measure to keep the secret of the brick and also because of the jealousy of the king, who wanted to prevent him from making a more beautiful palace for another king. Hence the Arabic phrase Senemar's compensation, Jaza as-Senemar. But well, in the real history, well, those of you who have traveled to Venice might have been amazed by the beauty of St. Mark's Square and its majestic bell tower. What you might not know is that this Campanile Tower has been destroyed fully in 1902, and what we see today is not the ancient tower that was nearly a millennia old, but a replica that was rebuilt in 1912. The original tower took more than 200 years to be built to the current height, and it was built mostly as a watchtower. Later in the 16th century, it was turned into a bell tower, and it has been damaged several times during its lifespan, mostly because it was struck by thunders. So poor conditions of the base was observed in several restorations in late 19th century, showing excessive settlement of the base. But what caused the collapse was the restoration that was done in 1902, where a decaying wood beam was removed and was replaced. Towers started shaking and trembling during the installation of the new beam. And so markers were installed to observe if the tower is shifting. And well, those markers, well, they were all broken. There were glass markers there. And it showed that the tower is shifting rapidly. And so a few days later, large cracks started to appear on the northern side. That resulted in a committee to be formed to study the situation of the tower. And that committee decided that the tower is structurally safe and is not a threat. So they just barricaded the plaza to prevent falling mortars from hitting the tourists. Just 2 days after that, the engineering committee labeled the structure as safe. It collapsed. So just a simple lesson to be learned here, and that is don't remove an element that is under load. You have to unload it first, ensure it, and this is actually the triggering effect in the collapse of the Metropole building that we saw earlier. The collapse of the zoology building of the Aberdeen University in Scotland is the first recorded instance of a progressive collapse in a steel frame structure. The building was a 6-story tall building, and it had a steel frame with concrete floors. The collapse happened during the construction when a handful of construction workers were working on it during a severe wind. There were investigations by the Sheriff of Scotland and also the Parliament of England, neither of which I could find in the UK National Archive. But the newsreels mentions a summary of the report claiming that the faulty connection welds were to be blamed for the collapse. These welds failed by fatigue during a severe wind, leading to a loss of lateral stability and collapse of the floors. On the top picture, you can see the floors sandwiched on top of each other. And the building was later rebuilt with almost the same blueprints at the same location, and you can still find it there and it's still in use. I would have loved to see the official report for this collapse because it seems curious how the connections that have experienced only a few cycles of loading during their short lifespan have reached the point of failure by fatigue. And I wanted to see also if there has been any temporary bracing during the construction that might have prevented the collapse. But well, it seems that anyhow, if either of these two have been considered, like if there have been a temporary bracing, or if the connections have been designed for fatigue, this could have been prevented. This is the event that had a huge impact on the whole concept of progressive collapse, and that is the collapse of the Ronan Point building in London in 1968. The building was a tall 22-story residential building built by tilt-up large panel precast walls and slabs, and it was known at the time by the name of the Danish contractor company Larsen Nielsen. And they were the company that invented the system, and that system was used thoroughly all around Europe at that time and even till the 2000s. That was a perfect choice for that era, since almost a fourth of the residential buildings in the United Kingdom were destroyed during World War II, and there was a dire need for mass construction of residential spaces. At the same time, large number of workforce have moved into industrial jobs, leaving a shortage of construction workers. So several buildings similar to this were being built all around the United Kingdom, 5 of which at exact the same time with the exact same design. And the collapse happened just 2 months after the building was populated. A small gas leak in the 18th story caused a small explosion in the kitchen. And this explosion was so small that it didn't even hurt the ears of the tenant who was there. Didn't even hurt the kitchenware that was in that kitchen. But this small explosion blew out the precast wall on the southeast side of the flat, and losing their support, the upper floor walls dropped down one after each other and so the weight of the floors 18, 19, 20, 21, they all fell down on the 18th floor and then caused the floor 17 downwards to collapse. And it was lucky that it happened very early in the morning, and most of the tenants were sleeping in their bedrooms, which was on the other side of the building. And actually, the building being populated just recently, well, some of the flats were still empty, so the casualties was limited to 4 persons. It was later shown in the investigations that the explosion was a very small one with a maximum pressure of only around 70 kilopascals. The problem was that the panels were not duly connected to each other, and they were supposed to be bolted and mortared, but due to bad workmanship and the lack of inspection, the bolts were not tight, and most of the connections were not mortared there. And so, what happened is that the building was actually relying on the friction between the wall and the slab to stay stable. And that smoke explosion was enough to raise the roof a little bit, and losing the friction, the wall fell out and the entire building came down. It was later shown that the building was designed to a wind load of 100 kilometers per hour. And at that location, at that height, winds of up to 170 kilometers per hour would have been expectable. So even if that explosion had not happened, the later strong wind would have caused the same collapse in the building. Um, so the lack of interconnectivity of the panels and low redundancy of the system meant that there was no alternative load path when a single wall panel was removed. Later, a few years later, that was observed that the building is experiencing some large deflections, and to the level that smoke or even sheets of paper or coins could have been slipped under the walls or through the joints and the slabs. And so this building and all those similar buildings that use the same technique were destroyed about 15 years after being built. Possibly the best documented building collapse in history is the collapse of World Trade Center in 2001. And I apologize again if watching this video is too painful for some participants. And what happened was that two Boeing 767 coordinately hit the two towers in upper floors, the north tower between 93rd and 99th floor, and the south between 77th and 85th floor. Buildings stood the early damage of the plane impact, but later collapsed because of the fire from the plane full tank of jet fuel. South Tower collapsed less than an hour after the impact, and the North Tower stood a little more than 2 hours. Nearly 2,600 people died in the incident, and that was an event that scarred the USA nation and had long-lasting effect in many other locations around the world. So there have been several investigations were done on this building, including one by Professor Abul Hassan Astani that reported to the Congress, and there have been other investigations by FEMA and NIST. And well, among them, Dr. Astani did not have access to the blueprints of the building, so some of his analysis were based on general information of this structure. The NIST report the NIST had more access to blueprints and construction data, so their report was more in depth. And it was shown that the building was structurally designed to stand an impact by a Boeing 707, which is an airplane with similar size and load of the one that hit the building. And although it was damaged during the impact, it stood still stable for 1 or 2 hours. And what caused the collapse was that apart from the damage to the structural elements, the thermal insulation on the elements were damaged in the impact that made beams and columns defenseless against the high temperature of burning kerosene. And if you know, kerosene can have an open air burning temperature of more than 1,000 degrees, while the steel loses its ability to carry loads in around somewhere 600, 700 degrees. So as the elements in one of the stories reached the plastic point, the upper floors crumbled down on the lower floors one by one, and making the horrible scene of the domino collapse of the building you just witnessed. A progressive collapse that similarly scarred the Iranian nation was the collapse of the Plosco building some 7 years ago in 2017. And it was once known as the most modern building of Tehran. And Plosco was a 16-story tall steel structure that, for a short period, was the tallest building in Tehran. It was claimed to have a lifespan of 200 years, but unfortunately, it didn't make up to 60. The lower picture shows how tall that building was at the time of construction compared to other buildings in Tehran. You might also notice that small white dot at the end of the view, and that is the Hotel Hilton, which is in this picture is way out of town, but now is just inside the town at the Parkway Cross. Fusco building was made of two parts, a tall office building and an extended shopping mall beneath it that once used to be a glamorous place, but in later days it became a textile market. The office building was also mostly used as a storage or workshop for textile vendors in later years. It was shown that poor maintenance of the building was a major factor in its collapse, as there were no working sprinklers, no firefighting equipment of the buildings at the time it collapsed. The incident that triggered the collapse of the building was a fire, possibly because of electric wires that started early morning in 10th floor. It was lucky that it happened on a holiday and no shops were open at that day. No shoppers were inside it. So but the building was full of textile, so the fire spread rapidly. Firefighters tried to stop the fire from spreading, but the building finally collapsed after nearly 3.5 hours of burning. And it took 16 firemen and six civilians in what became a long period of mourning in the country. This is how it happened. First, the northwestern part of the 11th floor above the initial fire at the 10th floor collapsed, following by the collapse of the same location in 12 and 13th story 10 minutes later. And then half an hour later, 10th floor collapsed almost fully on the 9th floor and a quick succession from there to the ground. And although I know it's painful to watch, please watch this video carefully and notice how the internal columns stood when the floors were falling down. You see that those columns in the middle, they're standing still. And here you can see the collapse of the building from another angle. And this better shows how this floors collapsed one on top of the other. The investigation showed that the building elements were all built-up sections, and the perimeter columns were two channels connected with plates at intervals, and the four internal columns were built by four channels connected with interval plates. The beams were mostly trusses that were in a manner that once was customary in Iran, known by the name of khorjini or saddle connection, and it was still used when I was became an engineer at my early years of working, but fortunately, it's now extinct. And what happened was that there were no fire or smoke barriers in the building, no fireproofing covers on the structural elements, and the poor maintenance of the building meant that there were no sprinklers and no working firefighting equipment. Studies showed that the first element to collapse were those small angles under the trusses because they were like the thinnest steel elements in the building. So they lost their load bearing ability. The trusses fell down and the floor fell down, and that is why you see that the floors were falling down while the column was still standing. So let's get to this most recent case at hand, that is the collapse of Francis Scott Key Bridge in Baltimore. The bridge was named after an American lawyer and poet who is the author of the lyrics to the Star Spangled Banner, that is the USA national anthem. The bridge is, or rather say was, an important infrastructure with not only local but also national importance, as the waterway is the path to the Baltimore port, that is one of the top 20 busiest ports in America. It is estimated that the port handles more than 50 million tons of cargo, which is worth more than 80 billion US dollars each year. To get a scale of this number, you might note that the Port of Vancouver, the busiest in Canada, manages around 120 million tons, a little bit more than two times that Port of Baltimore. The bridge itself connects the city to an industrial area and a county of more than 500,000 population. And the more than 30,000 vehicles pass the bridge daily, including 3,000 trucks. The collapse of the bridge was the result of it being hit on the southwest pier by a container ship named Dolly. That is a medium-sized ship by today's standard, but still a huge ship with gross tonnage of more than 91,000 tons. The ship, owned and operated by Singaporean companies with Indian crew, left the port a little after midnight, and it had some repairs the previous day at the port. A few minutes later, after departure, it went into a complete blackout that left it both without a working engine and without navigation. The captain sent out a mayday call and dropped the anchors in an effort to stop the ship, but you might notice that the huge momentum of a 91,000 ton ship, and notice that when we are in the water, there are no frictions to stop any movement. So ships tend to go a straight line, and stopping or changing their direction needs a lot of effort. The following the Mayday call, the traffic was stopped on the bridge, first on the north lane at the same time minute as the Mayday call, and the south lane a minute later. Fortunately, there were almost no passing traffic when the bridge collapsed, but there were 8 construction workers doing some repair job on the bridge, and they just stopped working and did not leave the bridge. And so at 1:28, when the ship hit the southwest pier of the bridge collapsed almost in a very quick succession of events. And out of those 8 workmen, only 2 survived. So here's what happened. First, I suspected and argued that the sequence of failure has started by the southmost support of the steel truss having moved out of the concrete pier and fell down. But watching several other movies of the incident showed me wrong. So the first thing to happen to the bridge was the collapse of the southern pier. And this caused the truss to have a much longer span and also the middle span to lose its arc action. The combination of this losing the arc action and having a longer span caused two elements on the southern side of the bridge to fail. And this meant that the bridge later was acting like a cantilever from the northern pier, which well it couldn't bear that much load. So a top elements on the bridge near the northern side then failed, and this made the bridge to fall down on the middle and the northern southern side. But also the kickback of this fall also made the northern span of the pier to not only fall down but also hit the concrete spans behind it, and so there were also three concrete spans also falling down after this collapse. It is too early to give a definitive response on why this happened. But two things are obvious. And first is that the ship size and the load during the design and construction of this bridge in the 70s was much smaller than what we have today. And it might be the reason behind the dolphins looking too small compared to the ship. And so the incident also happened at midnight, which is the time of the high tide, and the water level is too high, making those small dolphins even less useful. But it shall be noted that there are very few structural options we might have for bridges passing over such wide waterways, and it might not be possible to provide enough redundancy or reserve the strength that might be enough to stand the huge load of that impact from a ship. And I guess that the possible aftermath of this accident might be more emphasis on present offenders, dolphins, or protective islands around the piers of major bridges. One more recent collapse that you might have heard of these days is the collapse of Copenhagen Old Stock Exchange building. The iconic building that is pictured in the left by my dear friend Ali Fanud was under restoration when a fire happened inside it, causing the iconic tower and part of the building to collapse. I just wanted to note that this was not a progressive collapse, and it was just an ordinary effect of fire on a mainly wooden structure. And fortunately, there were no casualties, and most valuable artworks in the building have already been removed and saved. If you're interested in this subject, there's a very in-depth report on the collapse of another building, Champlain Tower South in Surfside, Florida, that collapsed a few years ago. And the report is by NIST, and it follows the incident second by second thanks to the many security cameras and that were in and around the building. And it shows how the collapse of a pool outside on the underground parking caused a domino effect on the columns of the building that finally brought down big parts of the building and killing nearly 100 residents. So enough of these horrible accidents. Let's take a look at what we can do to prevent it. In Canada, as far as I looked, I didn't find a specific code or guideline for the prevention of progressive collapse. and it is assumed that some general phrases in MBCC and design codes will provide enough provisions to prevent it. But there are two major publications directly focused on this subject in the USA, one by the General Services Administration, and that is overseeing the design of public buildings, and the other by NIST. U.S. Army and U.S. Foreign Secretary have also guidelines for the design of military facilities and the embassies. But later in this presentation, I will mostly quote the GSA guideline, the one that is on the left. Generally, there are four paths to preventing a progressive collapse and to encase an initial incident to a local limited collapse. The first is um, to add redundancy and alternative load paths to the building, and this is what is emphasized by most guidelines and codes, including the GSA and the Chapter 21 of Iran's National Building Code. Some other codes, including that of the U.S. Army, looks for more additional strength and ductility, and those like ACI 318 or CSA 821 mostly focus on interconnectivity and integrity of the structure. But it shall be noted that in some cases, none of these structural measures would be enough, and we would need some non-structural measures in place. Generally, redundancy is to have alternative load paths. So when some of the structural elements fail, there are others to cover for them. So, like, you might notice one of the early pictures of the Ronan Point building that shows that although the roof slab has lost its support that was being supported by some walls below it, but it's still kept stable by the cantilever effect of the parapet walls on top of it. And this alternative load path is what is required by GSA and Chapter 21 of the Iranian Building Code. And I shall add that these seismic codes of both United States and Iran have a redundancy factor, and so there's a punishing factor of 1.2 or 1.34 buildings that lack enough redundancy. That factor is not seen in the NBCC 2020, although there are some measures of it for irregular buildings, but that doesn't directly address the redundancy of buildings. So the presence of these measures of redundancy, integrity, and reserve load bearing capacity has shown to be successful in preserving the overall stability of the building. The picture shows the building known as the Bankers Trust Building, currently a Deutsche Bank in New York, which was just adjacent to the World Trade Center building. And it was hit hard with the debris from the World Trade Center. And although it lost some of its structural elements, it stood still. Here's what the GSA guideline says about the redundancy. It asks for an alternative load path in a way that removal of any single element will not cause a collapse in the structure. A similar provision is mentioned in the Chapter 21 of the Iranian Code, the so-called Padafand Ghair Amil in Farsi. And some claim that this might result into having more structural elements located in shorter spans. And although this is a good idea generally, it shall be noted that in some cases, like the bombing of Alfred P. Murrah building in Oklahoma, this wouldn't have been effective. So what happened in 1995 bombing of the Mara Federal Building was a van full of explosive driving into the building, taking out a major column that supported a supporting beam on which the columns of higher stories were sitting. And you can see a part of the frames on the right side of the picture, and I highlighted them in red on the right copy of the building. And excuse my lousy drawing skills. And it was first suggested that having more columns, like adding the one I showed in green, would have prevented the collapse. But it was later noticed that the explosion was so large that even if there were more columns more closely located, the blast would have taken out several columns at a time, bringing the same results. Um, I think okay. There have been extensive studies of the World Trade Center collapse, and they have showed that the building was well equipped with all we have spoken of. The outer tube of the building was highly redundant, it was extremely well interconnected, and had a very high level of ductility. The problem was that the load of the fire was too much for the structure to stand, and there was nothing a structural engineer could have done to stop it. The very fact that the building stood after the impact while bearing damage to some of the structural elements is a good testimony to this claim. A solution that is noted by both the GSA and the US Army is to have reserved strength and ductility. And this is mostly to face the consequences of a blast. And the provisions are very similar to those we have in seismic designs. And these provisions ask for better confinement of concrete, especially at the locations of possible plastic hinges, and a stricter check of the brittle fractures, and providing more ductility. And in this photo, you see a residential building in Bronx that collapsed in December 2023. And you can see how additional load-bearing capacity of the roof slab has helped it remain stable even after losing one of its supports. The incident is a painful reminder of consequences of engineering negligence. The engineer that oversaw a restoration labeled a load-bearing column of the building as non-load-bearing and removal, resulting in the collapse. We can see a lot of examples of how this reserved strength and ductility have been helpful in keeping a building stable at the face of an accident. The picture shows the aftermath of the 1993 bombing of the Norton Tower of the World Trade Center. A car bomb not unlike what exploded in the Alfred P. Murrah Federal Building of Oklahoma, blasted part of the underground levels of the tower. And those terrorists' intention was to cause the full collapse of the North Tower in a way that it will smash into the South Tower, thus destroying both. Fortunately, that didn't happen, and the structure was strong enough to only experience limited damage to the underground area without any major effect on the overall structure of the building. Well, as I told you, Canadian codes mostly talk about integrity, and here you see NBCC 2020 and its commentary. The National Building Code of Canada asks for the building to have sufficient integrity, and the commentary defines the integrity as the ability to absorb local failure without widespread collapse. NBC doesn't go into the detail of how this might be achieved, and it might be because the Canada being a relatively safe country, the Code Authority is not worried about terrorist attacks as the American authorities are, and thus the phrase may reasonably be expected. Sorry, what happened? Okay, the I was saying that the phrase may reasonably be expected does not cover extreme situations as bombing or terrorist attacks, as those incidents are not reasonably expected here. Um, the Canadian design codes also cover provisions for integrity. And here you see the relevant phrase from the CSA 823 for the design of concrete buildings, where it mentions integrity and focuses on slabs, precast structures, and especially tilt-up structures. And it is expected that with these provisions, we will not experience collapses like the Ronan Point and maybe that collapse of the Ronan Point and the deficiencies of many tilt-up precast structures in Europe has affected the CSA to have special focus on these structures. So the provisions ask for better interconnectivity of the panels and asks for effective ties between the elements. It especially addresses the base fault of the Ronan Point building by defining a minimum out-of-plane and horizontal load on the connections. There are many occasions where structural measures are not enough, as the cases of the World Trade Center and the Baltimore Bridge, and even to some extent the Glasgow building shows. That is, when we face an extremely large blast, an extremely heavy load, or a long burning fire. And in those occasions, we will need non-structural measures like the fire barriers or the firefighting equipment or the barriers that would prevent the explosive devices or the barriers that would prevent the collision. And in this picture, you can see clearly where how this is considered. And this is the Sunshine Sky Bridge in Tampa Bay, Florida. And the bridge on the right is the old Sunshine Sky Bridge that collapsed in 1980, and an incident that was, well, not unlike the one we had in the Francis Scott Key Bridge in the Baltimore. So a large ship hit the bridge on the pier, and so the central truss collapsed down. So and you see that when they built the new bridge on the left, which was finished almost 7 years later, now we have a lot of protective measures. We see huge dolphins there, and we also see the protective islands around the main two piers in the middle of the road. And I think that this is what is going to be the norm for the waterway bridges from now on. So you might wonder why at the beginning of this presentation I talked about resilience and how it relates to the progressive collapse. And this is where our main responsibility as an engineer comes to light, and that is to keep the public safety paramount in all we do. And look at the example of the Francis Scott Key Bridge. There were like thousands of cars and trucks passed this bridge daily, including some trucks carrying hazardous materials that would otherwise be unable to use the two tunnels at this location. And so also there were like 80 billions of dollars worth of cargo that was passing in the waterway and now need to be rerouted to other ports. This drastically affects the local economy. The bridge was the main access to the Hawkins Point industrial area. I guess it was probably the only access to it, and also the main access to the Anne Arundel County with a population of around 600,000 people. The reconstruction is going to take around 7 years and at least 400 million. But if you follow the news, you will know that it's going to take many more years for the politicians to include the budget and sign the permits. And by then, the costs will have risen several folds, like what we recently saw in the Quebec Bridge connecting the Ile d'Orléans to the mainland. And that was supposed to cost around 500 millions, and now the final estimates are close to 2.7 billions. This shows the importance of urban resilience and how the engineer is responsible to consider the larger effects of their work on the public. It also shows the importance of the professional ethics, as we see in the case of the recently collapsed building in Bronx.
He is the engineer blamed for the collapse of a Bronx building back in December.
And with this grim notice of the possible responsibilities of an engineer in the face of a collapse, I finish my presentation, and I shall thank you all for your notice and thank the Mohandas Civil Group for hosting this session.
Thank you, Nader, for very informative presentation and the good information that you delivered here. Do you need some time to have a break or something before Q&A, or you are ready to go?
Well, I already had my tea, so I'm ready to go.
Okay. I would like to ask Ms. Saadati Nejad, leader of the civil group, to take over and conduct the Q&A session.
Thank you, dear Afshin. I greatly appreciate it, Nader Jan. I greatly benefited from your speech. We all really enjoyed, and I'm sure everyone has enjoyed as well. I don't want to waste any time, so I'm going to invite everyone to participate in question and answer section. So please feel free to put your invaluable comments regarding this presentation or ask your questions.
Okay. May I ask a question if no one else has already raised hands? Yeah, this is Arsalan Mohajer. Although I'm not a civil engineer, but I'm very curious about the integrity of all these buildings and the consequence of the collapse, mostly due to fire. So my question is that whether the concrete building would have a better chance of survival compared to the steel frame, obviously, and what can be done to reduce this collapse due to the fire or dynamic loading, whether concrete would behave better with shear walls that they have.
Well, generally speaking, the concrete structures are safer in times of the fire, but well, that depends on the fire load that we're going to have and how long the fire is going to be burning. Because if the fire keeps burning like what we had in the World Trade Center, the temperature of the structural elements would finally reach the level that they cannot bear any load anymore. So when that is somewhere around 600, 700 degrees. And if both the concrete and steel, they will lose their strength at that level. But well, the good thing for the concrete structures is that we have some concrete cover, preventing the rebars to reach that fire that early. But if either of these buildings have been designed correctly and have fire barriers that would prevent the temperature from reaching the structural elements, they both can be safe, as well we see in the case of almost every building we see around us. But considering the lack of this temperature insulators, then the concrete is safer by itself.
If I may ask a follow-up question, these days, the mass timbers are becoming fashionable. And even in a museum in Chicago, the Architectural Museum, they're encouraging to go even high-rises now with mass timber. So how safe are they? and what can be done to protect them better?
Well, they are almost safe because they are not normal like jungle wood that we would see. They are treated wood and they are measures to prevent the fire to them. But then they would too require some sort of fire barriers to prevent them from experiencing high temperature loads. But if those barriers are considered, they can be also very safe.
Is there any height limit you would suggest for that type of structures? I mean, how high they can go?
Honestly, I'm not much familiar with the wood structures.
If there is no other question, may I jump in and ask another question? I was very
Sure, go ahead.
curious about this 3D printers that nowadays print houses or structure.
Yeah.
Again, how safe they are and how high they can go.
Well, generally speaking, again, they are almost safe, but well, those technologies that I see currently, they are mostly like mortar laying machines we see around ourselves. So I might say that the current technology wouldn't be suitable for very high-rise buildings, probably a few stories tall so far. But well, definitely if they show their value, we might see some new technologies that would bring more ductility to the building, because the ones we see are not very ductile, and they're mostly suitable for shorter buildings. I don't expect to see them in high rises anytime soon.
I see. So it's the ductility you need because of the dynamic load.
Yeah.
Yes. Okay. Sure.
So when the are taller buildings, they would be facing both the lateral loads from wind and earthquake,
Yes.
and
Yes.
for that we would require the ductility.
Okay.
Thank you. Afshin, go ahead.
Thank you again, Nader, for a very good and very informative presentation. I confess that what I'm about to say is somewhere between statement and question. So I would describe my thoughts, and I would appreciate if you say a few words in that context. You see, you showed us that a lot of codes ask for redundancy and interconnectivity.
Yeah.
But the question is, what exactly is redundancy? If I put so many columns in one side of the building, does it do? Or if I put so many internal connections between several parts of the building and leave the other parts untouched, does it do? And I would like to open the discussion of compatibility of deformations. Every structure works based on compatibility of deformations. I mean, other than the simple span structures, the hyperstatic structures work based on compatibility of deformations. Each and every element, structural element, changes its length, its torsional orientation, its bending orientation, and when it meets other structural elements, they have to somehow work together. That's called compatibility of deformations. And by redundancy, we are asking for the what-if scenario. What if this one column fails? What if this one beam fails? What happens? What exactly happens is that the compatibility of deformation, the configuration changes, and every other structural element comes to another state of equilibrium. So what is the question for structural engineers? Is number one, to ask the what if question and then find the right solution for that scenario. And sometimes it's not possible, or it is not economically feasible to make that the structure that withstands every predictable scenario. But at least we have to provide life safety. It means that enough time between beginning of failure to total collapse of the building that people can go out. And again, I would like to open the discussion about the compatibility of deformations. And this concept also applies to the forensic engineering. Whenever a collapse happens, a team of forensic engineers come to find the reason for collapse. So if you would please weigh in about this concept of compatibility of deformations.
Well, that is exactly what we do when we're analyzing different scenarios. Actually, that GSA guideline asks for the redundancy to be distributed all through the plan and all through the height of the building. So just adding a redundancy in one side of the building is not going to help other parts of it. But we exactly do the same. So we just start to take out elements one by one and see what would be the deformations and what would be the new load distribution in the system. And it's going to be a very difficult thing to do. It takes a lot of time if you have to do that. I had to do it for a certain government building back in Iran, and this is something that takes like many days to take out the columns one by one to see what happens and if the building would reach the level of collapse. And of course, what you mentioned about the compatibility of the deformation is the tool we would use in the analysis of these cases.
Thank you. Anybody else wants to weigh in? We have a lot of structural engineers here. Again, I would like to open another discussion about the alternative measures. Alternative measures are not always structural. Sometimes are about concept design. For example, in this bridge, if the clear height of the bridge was different, a little bit more, or the arrangement and strength of those dolphin structures in the water was a little bit stronger, and they don't always need to be strong as resisting the impact, because as you mentioned, when the ship weighs like 100,000 tons or even more and is traveling at just a couple of knots, maybe 10-20 kilometers per hour, that will produce a huge amount of impact energy. So instead of absorbing that energy, we may design some structures in the water that will divert the incoming force, the same as what we do in roads for guardrails. So I would like to open the discussion about concept designs. Sometimes when you design a building, you should consider that if something bad happens, what will happen to the neighboring building? Because if the buildings are too close to each other, collapse of one building might affect the others. Would you like to weigh in about this concept also?
Yeah, sure. About like the last comment you made about a building hitting another building, that is exactly what happened in the World Trade Center building number 7. And so the two buildings that were hit first were those two main towers, but the debris from those towers hit the building number 7, and that was one of the buildings that was totally destroyed during that incident. And so this is one of the indicators of how things like that happen. And as you noted, well, we predict that we're going to see more non-structural measures in certain infrastructures, especially those waterway bridges. And I expect that we're going to see more stringent provisions for dolphins and especially fenders, because those are the things that they just, as you said, would divert the ship from the collapse. And I just mentioned slightly the guideline of the U.S. Foreign Secretary for the design of the embassies, and actually, this is what they're looking mostly. They consider that their embassies have to have several barriers preventing any possible explosive device from reaching the building. So it's not just that we're going to design the building for the collapse or to have redundancy or additional strength. It's that we're going to have different barriers to stop the explosive to reach the building. And I think this is something that would be the norm for these sort of buildings all around the world.
Okay, thank you very much.
Thank you.
Hello, that was great and instructive for us. And I had the same question like Action. I think it's the time that we have a code or regulations to use the barriers around the bridge, especially. I wanted to ask this question that Action asked you. And I want to say that was a great presentation and perfect. And thank you so much for your presentation. Thank you.
Thanks a lot. Well, I just have to add about the bridges that passes waterways is that a very small percentage of the incidents of these bridges is the collision with the ships. So this is probably why there haven't been done enough study on it, and the codes are not that stringent on it, because this is I remember looking at it, and I think it was something around 3% of the collapses of those waterways are because of a ship hitting a pier. So the codes are mostly focusing on those 97 other percent of incidents that might happen, not those 3, but probably because accidents like these would attract a lot of attention. We might see some more stringent provisions later on.
Yeah, if there is no one to ask any question, I want to wrap up the presentation. And thanks again to Nader for his beneficial presentation. We are really enjoyed. Thank you so much. And
and I would like to thank everybody who participated. We do our part in providing these meetings for general public, and you do your part by participation. So I thank you for supporting us and participating in this meeting.
Yes.
Have a good night.
Thank you for organizing this.
Thank you.
Thank you. Bye-bye.
Thank you.
خدا نگهدار همگی.
شب بخیر.